Alrighty, so this is a video looking at the multiple choice section of January 2013. So let's get started straight away. A ball of mass m travelling at velocity v collides normally with a smooth wall as shown and rebounds elastically. Which line HT gives the correct expression for the change in momentum and the change in kinetic energy? So when it rebounds elastically, it's going to come out with velocity minus v. So the change in momentum is going to be minus mv minus mv, so it's going to be 2mv. And it's elastic, so kinetic energy is not going to change, making it answer A for this particular question. Alright, so let's move down. So what have we got here? We've got a cricket ball of mass 0.16 kilograms travelling at a speed of 35 meters per second. It's hit by a bat and as a result of the impact leaves the bat in the opposite direction at 30 meters per second. The impact takes 52 milliseconds. What is the average force on the ball? So the change in momentum would be 0.16, 35 minus 30. So that's a change in momentum. We've got the force, we need to divide that by the time. So let's put that in the calculator. And it comes out as a nice round number. It's 200 newtons, which is option D. Okay, so let's move. A ball is released so it falls vertically. The graph shows how the resultant force acting on the ball changes with time. Which one of the following is represented by the area under the graph? So the area under a force time graph is the impulse, or the change in momentum. So that's going to be option D. For a particle moving in a circle with uniform speed, which one of the following statements is incorrect? There is no displacement of the particle in the direction of the force. That is absolutely correct. Never gets closer to the centre. The force on the particle is always perpendicular to the velocity. That's true. That is a centripetal force. Velocity of the particle is constant. That's false. Speed is, but velocity changes. Kinetic energy is constant. Yes, it is. That's a scalar. So it's option number C. A revolving mountaintop restaurant turns slowly, completing a full rotation in 50 minutes. A man sitting in the restaurant 15 meters from the axis of rotation. What is the speed of the man relative to the stationary point? So we're going to be using V equals R omega, where omega is 2 pi over 50 minutes times 60 to turn it into seconds. 2 times pi divided by 50 times 60 gives you 2.09 but yada yada times 10 to the minus 3, and we times that by 15 to turn that into a velocity, so that ends up being pi over 100. Very useful if you have a calculator that outputs things in the simplest form first, like mine does, but if you calculate it you get the same thing. Particle of mass 0.20 kilograms moves with simple harmonic motion of amplitude 2 times 10 to the minus 2. The total energy of the particle is 4.0 times 10 to the minus 5. What is the time period of the motion? Okay, so let's have a look. So the time period of a mass spring system is given by this expression here. So what we need to do is work out K. So the energy stored in the spring at the amplitude would be half K times the amplitude squared, which would be the total energy there. So from here we can get K is going to be 2e over a squared. So 4 times 10 to the power of minus 5 times 2 divided by 2 times 10 to the minus 2 squared, which is a fifth. If we plug that into the equation, so 0.2 divided by answer gives you 1. Square root of that answer is 1 times 2 times pi gives you 2 pi seconds, which is answer D. With these spring constant questions, it's very common in these that you need to figure out what k is using some information they have, so it's a thing to look out for. The graph shows a variation in displacement with time for an object moving in a simple harmonic motion. Okay, what is the maximum acceleration of the object? So the amplitude is clearly 10 times 10 to the minus 2, which is 0.1 meters. And then if we look on our data and formula sheet, we can find an expression for the maximum velocity. So the frequency is going to be 1 over the time period, which is 1 over 2, or 0.5. So that's in hertz. So if we look at our SHM section of our formula sheet, A max is 2 pi f all squared multiplied by A. So let's do that. 2 times pi times 0.5 squared multiplied by 0.1 gives us a 0.99, which is option B. A simple pendulum and a mass spring system are taken to the moon, where the gravitational field strength is less than that on Earth. Which line A to D in table correctly describes the change, if any, in the period when compared to its value on Earth? So we're dealing with a pendulum. So time period is 2 pi root L over G. So if all the other values stay constant, if you decrease G, you should increase the time period like this, because it's on the bottom line of your equation. So that's going to eliminate C and D. Mass spring system is given by a different equation, so M over K. None of those involve the gravitational field strength anywhere, so that means this one isn't going to change, so it's going to be answer A. And looking at it, we could have actually gone straight to that one because it's the only one with no change in the answer. So we could have actually got that solution slightly shorter there. Two pendulums, well, whatever. P and Q are set up alongside each other. The period of P is 1.90 seconds and the period of Q is 1.95 seconds. How many oscillations are made by pendulum Q between two consecutive instants when P and Q move in phase with each other? Okay, so by the time Q has completed one full oscillation, the P pendulum will be 0.05 seconds into its new oscillation. So the P is ahead by 0.05 seconds. After two oscillations, it will be ahead by 0.1 seconds. And after three oscillations, it will be ahead by 0.15 seconds, etc., etc. So what we need is it to essentially end up so that P is back at the same point in the cycle. So what we need to do is take a full cycle of P. We need to know how many oscillations before it's back to the same point in the cycle. So you do the 1.90 divided by 0.95, which gives you 38 full oscillations before it's essentially one full swing out, so it's back in phase. So that's going to be answer B. A small mass is situated at a point on a line joining two large masses M1 and M2, such that it experiences no gravitational field force, or sorry, no resultant gravitational field force. Its distance from the centre of mass of M1 is R1, and distance from the centre of mass of M2 is R2. What's the ratio R1 to R2? So if we are equating their forces, I don't know, let's say the object is M. M2 M over R2 squared. So we've got M on both sides and G on both sides, so let's cancel those. We want R1 over R2, so let's swap these over. So we're going to get M1 over M2 is equal to R1 over R2 all squared. So then if we want to get rid of the squared, we'd have to square root this side. So it'd be root M1 over M2, which is answer C here. Which one of the following gives the correct unit for G squared over G? So G is the field strength of Earth in newtons per kilogram, which is being squared. And G, if we look onto our formula sheet, let's look up G. And it has the units newtons meters squared, kg to the minus 2. So what we end up with is newtons squared kilograms to the minus 2 all over newtons meters squared kg to the minus 2. So we can cancel kg to minus 2's. We can cancel one of the newtons and we end up with newtons per meter squared. So actually the unit of pressure, essentially. Okay. The gravitational field strength on the surface of the Earth is 6 times its value at the surface of the Moon. The mean density of the Moon is 0.6 times the mean density of the Earth. What is the ratio of the radius of the Earth to the radius of the Moon? So let's think the mass of the Earth is going to be equal to the density of the Earth times the volume of the Earth, which is going to be the density Earth times 4 over 3 pi radius of the Earth cubed. Mass of the Moon is going to be the density of the Moon times the volume of the Moon, which we know is 0.6 times the density of the Earth times by 4 over 3 pi r radius of the Moon cubed. And so we can match up the field strength. So we know that GME over RE squared is equal to 6 GMM over RM squared. So we can cancel the G's, and if we rule a line here, so mass of the Earth we know has this radius cubed. We're going to cancel it with squared, so we know these 4 over 3 pi is going to end up on both sides. So all we end up with is a term of radius of Earth on the left, and we end up with 6 times 0.6 on the top line, and by the radius of the Moon. So we want the radius of the Earth over that, so it's going to be 6 times 0.6, which is 3.6, which is answer B. So sorry if the working doesn't quite follow, there's not enough space. So what we've done is we've got calculated the mass of both the Moon and the Earth in terms of the density of the Earth. We've equated the field strengths to each other with this 6 factor because it's 6 times bigger, and we've substituted those values in to there and solved essentially and done some cancellation to find the answer. The diagram shows 2 points P and Q at distance r and 2r from the centre of a planet. Gravitational potential at P is minus 16. What is the work done on a 10 kilogram mass when it's taken from P to Q? So first of all, the potential at Q, it's essentially if we're going to double the distance, we will halve the potential, so it'd be -8 kilojoules per kilogram. And change in potential energy is m delta v, so it's going to be essentially so the change in potential is going to be 8 minus 16, because it's final minus initial. I'm going to times that by 10, and remember we've got kilojoules, so that's going to end up being 8 times 10, so 80 kilojoules, because remember it's always final minus initial, which is why we end up with a positive number, so you end up with not that one, answer C for this question here, by doing final minus initial. A small sphere of mass m and carrying a charge q is suspended from a thread and placed in a uniform horizontal electric field strength E. When the sphere comes to rest, the thread makes an angle theta with the vertical and the tension unit is T, as shown in the diagram. W is the weight of the sphere and F is the electric force acting on it. Under these conditions, which one of the following equations is incorrect? So if we resolve vertically, we know that T cos theta equals W. If we resolve horizontally, we know T sine theta equals F. And we know the force would be equal to the field strength times the charge of the object. So we know the first term is correct. Okay, so this third term here, we can see the tension squared would be equal to the force squared plus the weight force squared, so that's just applying like vector addition, so we're finding the resultant there, so that's going to be correct. We know that mg, the weight force, would be to eq cos theta, so we in fact know that this one is absolutely wrong, so this would be the one that is incorrect. Looking at this one B, mg cos theta and eq sine theta are essentially looking at the components of F and W in the T direction, so that one is going to be correct as well, just to double check. When a charge moves between 2 points in an electric field, or a mass is moved between 2 points in a gravitational field, energy may be transferred. Which one of the following statement is correct? No energy is transferred when the movement is parallel to the direction of the field. No. Energy transferred is independent of the path followed. Possibly there, yeah. The energy transferred is independent of the start and finish points. No, rubbish. If you change the start and end, you'll change the potential energy change. Energy is transferred when the movement is perpendicular to the field lines. Nope, that's rubbish as well. It's essentially the same thing as answer 1. So yeah, it was this one. The energy transferred is independent of the path followed. Only thing that matters is the change in potential. A beam of electrons moving with constant velocity in a vacuum enters a uniform electric field between two metal plates. Which one of the lines in the table describes the components of acceleration in the x and the y directions? So, the electron is going to be attracted upwards by the positive plate, so it's going to have vertical acceleration, but nothing in the horizontal direction. So which one? So the x direction is horizontal, so it should be 0. So let's eliminate those. And the acceleration, so the force is just proportional to the charge, so the force is constant, and so the acceleration will be constant as mass is constant. Okay, two charges each of 0.8 nanocoulombs are 40 millimeters apart. Point P is 40 millimeters from each of the charges. What is the electric potential at P? So we know that potential is calculated by doing charge over 4 pi E0R. So let's do those here. So the charge is 0.8 times 10 to the power of minus 9, because it's a nanocoulomb, divided by 4 times pi times 0.85 times 10 to the minus 12, times by 40 times 10 to the power of minus 3, which is equal to 180 volts. However, there are two charges, both of which are trying to accelerate it, so that's going to get multiplied by 2, ending up with 360 volts. Initially uncharged capacitor of capacitance 20 microfarads is charged by a constant current of 80 microamps, which line A to D gives the potential difference and the energy stored in the capacitor after 50 seconds. So to get V, we would do Q over C. So we need to work out Q, which would be 80 microamps times 50, which is 4 times 10 to the minus 3. Let's divide that by the capacitance, 20 times 10 to the minus 6, which gives you 200, or 2 times 10 to the minus 2. So that eliminates the first two. So let's square that, divided by 2 and times by 20 times 10 to the power minus 6. So 200 squared divided by 2 times by 20 times 10 to the power minus 6, which is 0.4, which is answer D. Which one of the following statements about a parallel plate capacitor is incorrect? The capacitance of the capacitor, the amount of charge stored by the capacitor when a PD of across the plate is 1 volt. That is absolutely correct. So that's the definition of capacitance. A uniform electric field exists between the plates. Yes, when you have parallel plates, you have a uniform field. Charge stored is inversely proportional to the PD across the plates. No rubbish. The energy stored is proportional to the square of the PD, yeah, because it's half CV squared. So the answer we're looking for is C. A horizontal straight wire of length 40 millimeters is in an east-west direction as shown in the diagram. A uniform magnetic field of flux density 50 millitesla is directed downwards into the plane of the diagram. Okay. When a current of 5 amps passes through the wire from west to east, a horizontal force acts on the wire. Which line gives the magnitude and direction of the force? So the magnitude would be BIL, so 40 times 10 to the minus 3, where minus 3 is L, times by the current, so 5, times by 50 times 10 to the power of minus 3, gives you 1 over 100 newtons, or 10 millinewtons. So let's get rid of those two. And so what have we got? We've got the magnetic field acting into the diagram. We've got the current going to the right. So when we apply Fleming's left-hand law, we've got the force heading in the northerly direction because my thumb is pointing straight up. So answer B. Which line A to D in the table correctly describes the trajectory of charged particles which enter separately at right angles in a uniform electric field and uniform magnetic field? So in a magnetic field, they'll end up in circular motion. So because the force would always be perpendicular to the motion. In a uniform field, we'd be in some sort of parabolic path because the force is in a fixed direction, so it just accelerates in that component of its direction. So it's going to be answer A. Rectangular coil is rotated in a uniform magnetic field. When the coil is rotated at a constant rate, an alternating EMF is induced in it. A variation of EMF in volts with time is given by this equation here. Which line in the table gives the peak value of the EMF and the frequency of the induced EMF. So the peak would be 20, because that's what's multiplying the sine function. So let's get rid of the ones that don't say 20. And inside the sine function we have omega t, and omega is 2 pi f, so 100 is equal to 2 pi f. So 100 equals 2f, so f equals 50. So that's going to be answer C there. Magnetic flux through a coil is in 5 turns changes uniformly from 15 times 10 to the minus 3 to 7 times 10 to the minus 3 in 0.5 seconds. What is the magnitude of the EMF? So we need to find the rate of change of flux linkage. So we've got the flux changing from 15 to 7, so 15 minus 7 times 10 to the power minus 3. The change in flux. To get the rate of change of flux, we divide by time, so divide by 0.5. Gets 0.016, but we've got 5, so we've got 0.08 is the rate of change of flux linkage, and 0.08 is 80 millivolts, so answer D there. So what we've done there is we've calculated the change in flux divided by time, and we've times it by n, is essentially the strategy we've used. Which one of the following statements concerning power losses in a transformer is incorrect? So laminating the core reduces eddy currents, so that is a source to reduce loss. High resistance windings would be very bad because you're wasting a lot of energy, so that one is incorrect. Using a thick wire reduces the resistance, so that was good. Using a core made of special iron alloys which are easily magnetized is a good thing, so it will be answer B here. Transformer with 3000 turns in its primary core is used to change an alternating potential difference from an RMS value of 240 to an RMS value of 12. When a 60 watt 12 volt lamp is connected to the secondary coil, the lamp lights as normal brightness and an RMS current of 0.26 passes through the coil, primary core. Which line A to D gives the correct value for the number of turns on the secondary coil and the transformer efficiency? So if it steps down from 240 to 12, that's a step ratio of 20. So if we had 3000 turns, we're stepping down the voltage, so we'd end up with 150 on this one. So we're going to get rid of this one because it's a step down transformer. Okay, so if we're calculating the power in, so we're 0.26 is the current times 240, gives you 62.4 is the power in. We get 60 out, so let's divide 60 by the answer, and we end up with 96% efficiency there, so that's going to be answer A.